See program details. Go on, make a change. Make a break for it.
Conversations, the hot topic at 6:30 when the OU discusses cyber talk, the language of the digital age. And from linking communities to blitzing an eyesore. Now on BBC Learning Zone, a look at another benefit of modern technology.
Providing power on a national scale puts electrical materials to a civil engineering test. Delivering mains electricity means providing a continuous pathway from power station to socket. Much of that is done with wires and lines suspended overhead. But one commercial consumer moves around a great deal and needs something a little more flexible than a plug and socket. We'll see the materials challenges posed by these two applications.
As you may know, or have probably noticed from looking around the countryside, pylons come in different shapes and sizes. And that's a reflection of the size of voltage at which they're transmitting power. And this in turn is because they're using air as the insulator.
Without a good electrical insulator to separate the lines from each other and from the earth, it would be the electrical equivalent of a leaky water pipe. Wasteful, if not a touch hazardous. Air ought to be a pretty good insulator. It's made up of molecules, small clusters of atoms, strongly bound together by electric charges, but overall neutral, and so not able to transport net charge. Apart from price, there's another advantage to air. At full load, lines get rather warm. A few tens of watts per metre of heat are carried off from the cables by the air. How much air do we need for the insulation of the supergrid at 400 kV? In a car's spark plug, the gap at the bottom here is where the spark is formed. It's about 1 millimetre, and that needs at least 2 or 3 kV in air. Twice the gap would need twice the voltage to break it down and form a spark. Scaling up would suggest that 400 kV sparks could jump 200 millimetres or so. Put in an engineer's safety factor of 10, and we'd better not get within a couple of metres of one of the 400 kV lines. But that's with dry air. If it's raining or foggy, the insulation strength is nothing like as good, but you get the general idea. Of course, the weight and tension of the line must be supported by load-bearing connections between the lines and the pylon, and at 400 kV, the conductor must be no closer than 1 metre to the tower, or even the ground when it comes down to a substation. The loads may appear to be lighter here, but some of these insulators contain high-pressure gas. What's needed is an insulating material strong enough to hold its own weight and that of the cable and extra loads from wind and ice. What material would you use?
Two load-bearing materials that spring to mind are steel and concrete. We can't use steel though because we're looking for an insulator, and that rules out all metals. And concrete, though it's good in compression when you squash it, is not so good in tension. To work in tension it needs reinforcement, and the idea of reinforcing rods up the middle is not so good. Now, ionically bonded or covalently bonded materials are insulators. So the question is, can we make them strong enough for this purpose? Ever since the beginnings of the electricity supply industry over a century ago, porcelain has been a popular choice. But you can also use glass, and this is one that's been used. In a marine environment, it's not so good, in fact. The surface finish on the porcelain is particularly important for getting good insulation. But it's not just the environment that gives rise to pollution. When the pylons are painted, then they get splashes all over them, and they have to go on working even with that on. In fact, To deal with that, the underneath structure is given a particularly interesting shape here to try and make sure that there are always areas of surface which are kept free from pollution and other contaminants.
This pattern of insulator is designed to hang together with others to form a string. They're secured by a metal clip. And you can see the cement wedge construction of the fixing. Others, such as the hollow post insulators, are made in one piece. It's not just the surface finish that's important. The internal composition must be right too.
It looks like teapot material, and in fact it virtually is, though its microstructure is a good bit more carefully controlled.
Both electrical and mechanical strengths would be severely degraded if the finished product were to contain small pores and voids. But how do you obtain such a homogeneous structure from what are natural materials? Very fine particle clays are blended and formed into cakes. The clay cakes are then chopped up and compressed by the internal screw of this machine. This is an extrusion process, similar to that used in the plastics industry. Here, the material is extruded from a vacuum to ensure that there are no air-filled voids. These clay dumps, as they're called, are then dried until they have sufficient rigidity for the next operation. Although they may look like cylinders of modelling clay, they're in fact now dry enough to be machined. Smaller insulators are mounted on horizontal lathes, but the large post insulators for supporting lines on ground-based equipment are held vertically. It's here that the shape of the insulator begins to emerge as the excess material is removed in ever finer stages. The characteristic shape, the ridges are called sheds, ensures that a good length of surface exists to spread the electrical stresses along. When the system experiences a fault voltage, the tightly bound electrons in the molecules of the bulk ceramic material aren't the ones most likely to get released. It's those in the surface deposits and in the surrounding air which yield and lead to flashover. The exact shape is produced by following a pattern on the machine and then hand finishing to remove blemishes. Any sharp bits would produce sites where electric stress concentrations could arise, lowering the breakdown strength of the system. Another period of drying is followed by glazing. The glaze further enhances the smooth surface finish and, as we'll see in a moment, has another purpose. The firing stage is carefully controlled to ensure that maximum strength is achieved. These workpieces are being cleaned and stacked, ready to be moved into the kiln, where they will stay for a few days. During firing, once the water is driven out, the clay particles literally grow together. It's called sintering. Overcooking allows too much growth of the particles beyond that for optimal strength. The material density increases during firing as the final structure is more compact. These unfired units will shrink by well over 10%, so that after firing they're noticeably shorter. During firing, the glaze melts, forming a glass skin on the surface.
The glaze is important for two reasons. First, it provides a non-stick surface which is easily washed clean by the weather and stops pollution building up. But secondly, it provides also a compressive coat, and that tends to squeeze closed the tiny surface cracks, greatly aiding the strength. They only make to order though, so there's clearly a big project on here.
Apart from tests for porosity, samples will be selected for mechanical and other physical tests.
One of the biggest electrical problems for power systems is associated with voltage surges when there are switchings or lightning strikes to the system. Much of the additional ironmongery at pylons and power stations is associated with this. This laboratory is set up to simulate some of those high fault voltages. The large grey transformer behind me produces about 800 kilovolts, and that's further stepped up by the transformer standing on the insulating legs there, so that on the big sphere at the top over 1,000,000 volts can be produced. That's more than twice the surface voltage. A fine wire brings that potential down onto a conductor, or bus bar as it's called, which at the moment is suspended from the insulator under test. It's actually a post insulator, and it's over 4 meters in length.
After allowing visitors to make a safe exit, the high tension is switched on. With our TV lights switched off, you can see and hear the corona as air molecules are torn apart into charged fragments, ions, in the high electric field around the conductors. The voltage is increased until a flashover occurs. It's through the air, and the insulator survives unscathed, fit for another 40 years service. It's easy to see examples of these overhead lines, but they're just one solution to the grid's supply needs.
The line hasn't come to an end here, it's just come to a built-up area, and the cables have to go underground. So what do you think the materials problems are? Well, we can't use air as the insulator anymore, and we've got to allow for the fact that the cable gets warm when it's carrying current.
In domestic cable insulation, for 200 volts or so, a millimetre of PVC is satisfactory. But for hundreds of kilovolts, that would scale to a PVC cable of over 1 metre thick, hardly practical for installation. And there's the problem of removing some tens of watts of heat per metre. What we want is an insulator with a certain amount of mechanical flexibility and a reasonable thermal conductivity. Covalently bonded liquids, oils, mechanically stiffened with paper, are in fact the insulator inside this cable. We'll see how it's made in a minute.
So you put the cable into the trench and fill it up again. But you only get a fixed amount of cable on a roll, something like the length of this street in fact. And then you've got to joint two cables. And remember, this is an oil-filled cable, so it's a good bit more complicated than, say, joining an extension lead. This is one of the holes in the ground where the jointing is done. It's about 2 meters deep, 2 meters wide, lined with concrete. And in a couple of days' time, this is going to be turned almost into an operating theatre. They'll be cleaning it all up, and the gang will be coming in for a short period of time, about 18 hours, to start joining these cables. Here they are, 275 kV, this one, oil-filled cable, with 3 coming in that way, 3 coming in that way. We've got to keep the oil pressure on them all the time, and then they have to be cropped to length and the jointing proper. Yeah.
Preparation for the jointing gives us the ideal opportunity to see how the cable's made up. There's an aluminium sheath around the outside to contain the internal oil pressure and for other electrical reasons. The basic principles are just as in the early days in London. The insulator is oil-impregnated paper. It's hard to do better than this combination. This cable's rated at 275 kV and incorporates a hollow core between the strands through which oil permeates to assist the cooling. There are variations on this design which can use compressed gas or hardened plastics as the insulator. As well as being the electrical insulator, the oil can also carry heat away by convection, in contrast to polymeric solids, which are inherently poor conductors of heat. The centre conductors are copper. Here they're being scrupulously cleaned, with all paper debris being removed prior to making the electrical joint.
This is the ferrule, the piece that actually does the electrical connection. It's what you might expect. It's brass and copper, brass end caps on a main copper body here. And you put a conductor in from this end and the conductor in from that end, and then crimp the ends tight.
After some 18 hours hard work, the electrical connections and the hydraulic seals are complete and encased underground. Underground cabling can cost over 10 times as much as overhead lines, but not because of the cost of the materials. We've cracked that side of it. But for at least one user, an overhead supply is altogether different, and the range of materials more diverse. I spoke to Alan Bradwell from British Rail's Research Department at Derby.
What you'll see from trackside is structures at regular intervals supporting the overhead wire, a catenary, a contact wire, and a pantograph sliding along the contact wire. The overhead line voltage is 25,000 volts, and a typical small multiple unit will take about 40 amps, and a locomotive will take about 150 amps. The wire is not continuous, it's broken into sections for tensioning and for electrical sections. Every 2 kilometres the wire has a series of weights providing about 1 ton tension. The wire expands between normal low temperature minus 20 degrees C and the highest temperature about 60 degrees C. It expands about 2 metres, and the wire has to be sectioned about every 2 kilometres to allow for that expansion. Electrically, the overhead wire is broken into sections about 15 kilometres long, where power is fed in from the electricity board in through our feeder stations. The wire is supported on masts at centimetre intervals, and a stranded copper catenary is connected between the masts. Hanging from the catenary is a solid copper contact wire, which it hangs on droppers at regular intervals. Until the 1970s, we used an all-copper system, but with the rising price of copper, we investigated an aluminium catenary wire, an aluminium with 2 steel strands inside for reinforcement.
With 1 ton of tension in the cable, what do you do about creep?
On new wire there isn't much of a problem, but as the wire wears and becomes half worn, the creep becomes significant, and the copper contact wire is actually alloyed with cadmium to reduce the creep. Other alloys such as silver, which we might investigate in the future. Each train has a pantograph. The pantograph slides along the copper wire and eventually leads to this kind of wear in the contact wire. This is where probably after about 10 or 20 years. The overhead line, the copper wire in Britain lasts about 30 years. Each pantograph has 8 carbon segments, and the segments are replaceable and wear out in about 60 days, 2 months. The segments are made of impregnated carbon. Carbon is a good brush material. It minimises the wear on the overhead wire. But this particular carbon has copper impregnation to improve the impact strength against damage, and also to improve the conductivity to ensure that the current flows from the surface into the copper sheath on the back of the carbon. If the pantograph hits a defective part of the overhead wire, such as a displaced dropper, it may cause impact damage, such as we see on this carbon here. Most railways use a series of overlaps where the running wire goes out and a new running wire comes in and maintains mechanical continuity. On British Railways we use a glass fibre insulating section. This is the insulator. It consists of a glass fibre rod, very flexible. The insulator carries 1 ton tension. It has 25 kV across it, and the pantograph runs along the lower surface of the insulator, as you can see from the carbon deposited. It consists of a glass fibre rod, pultruded glass fibre rod, with a series of ceramic beads on the surface, and the whole body is impregnated with a silicone rubber to keep moisture from the inside and prevent tracking of the glass fibre rod. The end fittings are, in the past, the end fittings were crimped, but now a bimetal friction welded piece is made, and this is glued to the end of the insulator so that the pantograph can run straight from the contact wire straight across the insulator. Porcelain is the normal material for supporting the overhead line, and there must be over 200,000 of this style of insulator used on British Railways. Porcelain though is very heavy. It is fragile and can be broken by vandals or during handling, but it does have an indefinite life. The life is way in excess of 30 years. To tackle the vandalism problem, we've been evaluating polymeric insulators which use either a porcelain or a glass fibre core with rubber sheds moulded on the surface. And this is a typical railway insulator in use, a rubber insulator in use on the railways at the moment. We've also developed a clip-on rubber shed to prevent vandalism to conventional porcelain insulators. This will withstand any vandal throwing stones at it. Polymeric insulators consist of a glass fibre pultruded core with pre-moulded, in this case Teflon sheds, but many insulators have rubber sheds. This shows how the end fittings are connected to a glass fibre rod. In this case it's a bonded resin connection, and in this case the glass fibre has been split to provide a wedge to key into the end fitting.
Not all materials have the environmental stability of porcelain.
Polymeric materials do degrade, either due to sunlight or surface sparking. We test these in the fog chamber by applying salt solution to them, applying 25 kV and leaving the surface arcs to run up and down the surface, and slowly this degrades the polymeric material. These particular insulators that we have chosen have passed all the salt fog tests that we've done on them.
We've seen 3 different conductors: carbon, copper and aluminium, and a variety of insulating materials: the porcelain and the polymers, glass fibre, oil and oil impregnated paper, and the free air.
And you can find out how technical advances have changed the designs of bridges at the same time next week in Spanning Materials. The OU has a scheme allowing other organisations to record its programmes for teaching and training. For details, call 01908